Hello, everyone. My name is Mike Hillman. I'm an associate professor at Penn State University, and I will be presenting a nodally integrated RKPM formulation for three-dimensional printing, specifically deposition-based printing. This work is in collaboration with several people at Penn State. And my former student who's a professor now in Taiwan. So I'd like to thank the organizers for inviting me to give this keynote presentation and organizing the mini symposia. Okay, so what do we have to deal with if we want to try to do some simulation of three-dimensional printing, and again, specifically the deposition type. So here you can see this is thermoplastics being deposited and building up apart layer by layer. The individual beads or rods are built on top of one another. The material fuses to itself to build up the part. So another type of deposition 3D printing is using concrete. So this is work being shown here by Penn State, team here that's been doing this on the experimental side for quite a while. And I've been collaborating with them on doing some numerical simulations, as we'll see. Okay, so what do we have to deal with? Material flow, obviously. A big challenge for traditional methods would be topological domain changes. So these parts are being built up. So the domain is actually changing over time. And often in these types of technologies, we'll have to deal with thermo-mechanical systems, particularly for thermoplastics, but also concrete. Okay, so the approach that we've chosen to take is thermo-mechanical mesh-free methods, specifically a type of Lagrangian mesh-free method. So there's, several different approaches you could take. You could do Eulerian FEM and so forth. Now we're going to use the reproducing kernel particle method, or RKPM, which is a mesh-free method, and we'll use nodal integration. We'd like to keep everything at the nodes, state field variables, and so on. Much more natural to do things that way than try to deal with, say, a mesh and convecting things around. And for now, we're going to keep with explicit time integration, although I'll come back to that at the end of the talk. But all the codes that we've been developing, at least at Penn State in my group, are explicit codes. So we'll stick with that for now. Okay, so that's the framework, and we're going to stick with nodal integration. Again, you have the integration points coincident with the nodes, so everything is living there. So this is very natural for mesh-free simulations, but this is a type of under integration of the weak form. So we'll have to deal with stability or coercivity. And since we're under integrating the weak form, it turns out that we have to deal with convergence and accuracy for mesh-free approximations. Being very difficult to integrate in the weak form. And then something we need to keep in mind as well is to try to do these in an efficient manner. Obviously, you could just kind of go overkill and use a lot of integration points, but that's going to significantly slow down your simulation. Okay, so as some of you might know, I've done quite a bit of work for the purely mechanical problem, but how about for the coupled problem? Can we develop these same techniques for coupled thermomechanical analysis and by extension, similar PDEs? Okay, the other thing that we're dealing with is explicit time integration. So as you might know, if you're solving the energy equation or heat equation, more generally the energy equation, then you'll have to deal with this explicit time step restriction. So your time step will have to be less than this particular form, which includes the nodal spacing squared. So as you crunch up your nodal spacing, you're crunching up your time step, and generally explicit methods are considered prohibitively expensive for the energy equation. So you go with implicit, but we're going to try to do things explicit and see how that turns out. Okay, so I'll introduce the numerical framework, RKPM, talk about variationally consistent integration, how we achieve accuracy with particular emphasis on the coupled problem now. And same thing with stabilization. So we'll use NSNI and we'll pay attention to the coupled problem. Okay, then we'll get into thermoplasticity and then generalized thermomechanical theories of the hyperbolic type. So this will be more amenable to explicit time integration. Then I'll show some simulations and some of those details involved and with the conclusion. Okay, so we're using the reproducing kernel particle method. It's based on the Galerkin framework. You can go with strong form. We're going to stick with weak form now. So our approximation is denoted phi here. So we have the first term in black is a correction function to ensure the accuracy. And the second term in blue is the so-called kernel function, which controls the locality of the approximation. So you get a banded approximation and also controls the smoothness. Okay, a nice feature of this, I won't go into detail about all these unique properties, but you can get arbitrary smoothness, and this is uncoupled with the order of approximation. So you can get very low order with high order smoothness and vice versa. Okay, the first part that I mentioned is the correction function, which enforces the reproducing condition, so we can get completeness in our approximation space up to order n as we like, and again, uncoupled with the smoothness. Okay, and as I mentioned, we're using the Galerkin framework, so we'll have to carry out numerical integration. And when we deal with numerical integration, let's just take something very simple, straightforward approach and just use Gauss integration. So this is called a background mesh. We're just going to construct this mesh to carry out the numerical integration and do Gauss quadrature. Okay, so these don't have to be associated with the nodes. That's another detail I won't go into much. In any case, this is just a demonstration. I solve a Poisson equation with linear completeness. I look at the L2 norm of the air and look at the convergence in the nodal spacing H. So this is a log-log plot. If you look at the rate, you would expect a rate of 2. But we're using numerical integration, so we're committing a variational crime. We're not really solving pure Galerkin, the pure Galerkin formulation. So what happens? Okay, so I'm testing different orders of quadrature, 2 by 2, 3 by 3, up to 5 by 5 Gauss integration, GI here. And it turns out that you need very high order Gauss integration in order to get the optimal convergence rate. So here's 2 by 2, for example, you see it just stops converging. Okay, how about nodal integration? This is actually what we'd like to do. Well, I plotted this. We call this direct nodal integration when we don't do anything special. Just integrate directly at the nodes, and you get a convergence plot like this up here. And you can see that I also stop converging. So this is not good. This is something that we'll have to take care of. Another thing that we'll have to take care of is instability. So you'll get these almost like hourglass modes in FEM, where you're getting node-to-node oscillations in your solution. You can see very clear for this Poisson equation showing up here, where I should just get a very smooth solution, but getting these spurious node-to-node oscillations. So we'll see about stabilizing those. And again, trying to fix these two issues with particular emphasis on the coupled problem. Okay, so I'll just briefly overview the methods to address the accuracy and the one that we're choosing. So actually the source of the inaccuracy is fairly straightforward to show. You can plot the supports of the shape functions. I'm showing circular supports here in the dashed line. So you can see the supports form a very complex structure, right? And here's my background integration cells, say if I use Gauss quadrature. Okay, so basically in the weak form, I'm going to have the test function and the trial function, the product of those two, right? And you're trying to integrate all these little pieces, right? That's the interaction between the points, these overlaps, right? So you're trying to capture all these, and you can see why I need very high order Gauss integration to get good accuracy. Is I would try to get all these little overlaps and pieces, and one way to address that would be to align these cells. You can see that just the fact that these cells are not conforming to the support is going to cause a lot of problems. So let's see. Yeah, so there's several techniques, notably the MLPG method, which is really the spirit of these methods is to align the supports and the cells, right? And there's lots of algorithms that you can, come up with to align those. As you get into multiple dimensions, it's going to be obviously more complicated. In the paradynamics literature, one approach they've taken is to use the intersection of these integration cells and supports, and use partial weights depending on the degree of intersection. Okay, we're going to stick with something called variationally consistent integration, which was known as the integration constraint in the early 2000s. The generalization of that is in this paper, and this is a way to pass the patch test. So it kind of takes a step back and says, well, instead of trying to compute all these partial volumes or align the cells, I'm just going to look at what are the requirements to pass the patch test, or the higher order versions, and try to satisfy those. So you can do that in a variety of ways. I'll show one way, one simple way that we use in our research to satisfy those conditions. Now, I've added one more paper here. Recently, there's been an accuracy analysis showing that you really need this patch test condition to converge in the numerical solution of PDEs by weak form methods. So it turns out it's not just like an engineering approach that I want to pass patch test. It turns out to be very important to get the optimal convergence rate. So they recently proved that in this paper. Okay, so I'm talking about thermomechanical coupled problems today. So let's just take a simple model problem, linear isotropic thermoelasticity. So here's our equation of motion. We're going to use the Duhamel-Newman law, which gives the thermal strains affecting the stress. Okay, the other equation we have is the energy equation. So this might look very familiar, but now we have the mechanical term showing up as a kind of source term here. Okay, so that's how the two equations are coupled, and you can treat them as uncoupled or coupled depending on the problem constants. Okay, so let's look at this idea of trying to pass the patch test. I'll take just a very simple problem. I'll start with elasticity, then I'll go to thermoelasticity. Start with elasticity. I'll design this with a linear solution. Okay, if I have a linear solution, then my strain is constant and my stress is constant. Okay, so this is just a manufactured problem with a linear solution. So here, my exact stress is constant. I'm showing the shear stress here. Okay, let's solve it with some numerical integration techniques. I'll also use linear basis, which can exactly represent this solution, but it turns out not in the Galerkin equation, in the approximation sense, but not in the Galerkin sense. Okay, so here's my little integration, and here's Gauss integration one by one, showing that, well, wow, we are getting pretty far off from this linear solution, even though we can represent that with the basis. Okay, so what's going on here? I'll start with the equation of motion again. Okay, we can pay attention to the black for a second. So here's my linear solution generalized to nth order. This is multi-index notation, just indicates an nth order solution. Okay, here's my stress associated with that. So now I'm going to throw in the thermal field. I'll put that in red here. Okay, so I'll consider mth order solution for my thermal field. So that will come into my stress here. Okay, design this problem. This is just a standard way to manufacture the solution. Okay, here's my Galerkin method. And if I plug in these conditions, I use the completeness conditions, I consider that I can represent this solution, I will get this set of equations. Now, the first one is from some previous work showing what you need to do to get this nth order Galerkin exactness or pass that nth order patch test. And I'm denoting this first term here, the hat, which is the test function. So it's a condition on the test function. I'm also denoting the quadrature with hats on the integrals. So it's a condition on the numerical integration or quadrature in the test function. And if you look at this, you can identify this as an integration by parts with divergence. Okay, you'll have to satisfy this condition with your test function, your nth order solution, and your quadrature. Okay, this is been around for a little while now. So here we've added the temperature field and see what happens. You'll get one more condition on the test function here. Okay, in terms of the nth order solution of the temperature field. Okay, you can do the same thing for that energy equation. Plug and chug, and you'll get a condition on the test function that you're using for your energy equation. And again, the quadrature and the nth order solution of the temperature field. So, in hindsight, this this isn't a surprise, but takes some work to figure these things out. So these are the conditions. What I'm going to do is I'm going to look at a uniform correction. Just keep everything simple. I'll look at an mth order and nth order solution for the temperature and displacement respectively. Since they're both integration by parts conditions, I'll just unify them in one equation. Okay, then I'll just do a uniform correction on the test function for both the temperature field and the displacement field. Okay, so what we do, we know that it's a condition on the test function, so we'll introduce a correction into the test function. So this can represent, say, P unknowns, then I'll introduce P conditions, then I'll introduce P unknowns and try to satisfy these. So we can do that. So this is what the correction looks like for linear exactness, trying to obtain these coefficients here. This is in 2D. So you just plug and chug, and this turns out to be a very local correction. So it's actually very efficient. You can see these papers for discussions on that. Okay, so here's our patch test. Now we're doing it for static thermoelasticity. We look at a regular node distribution, which is kind of a challenge problem for meshfree methods. Okay, so you can see here, black, my linear solution, DNI, direct nodal integration in red, pretty far from the mark, and VC, variationally consistent nodal integration. You can see it matches with the exact solution, and you can confirm that with the L2 norm. Okay, and we can apply this to any other integration method that we like, so we'll come back to that later. Okay, let's talk about the instability. So this is fairly easy to show. You look at a sawtooth mode, +1, -1, and so on. You'll get a strain field that looks like this. Because of the fact that we've got a smooth approximation, you get a zero strain at the nodal locations. This is pretty easy to show. Okay, how about the strain energy density? Well, for this linear elastic rod here, you'll get something that looks like this. Okay, so here's the strain energy density. We're trying to integrate the variation on that in the weak form. If we use the nodes as integration points, you can see, right, the integration is just nothing but the area under the curve. You can see I miss all of this energy here in the middle. Okay, so this is what's causing the instability, and there's very little energy associated with this mode captured if you do nodal integration. Okay, so I won't get into all of the different methods, but obviously I could sprinkle some sampling points here and capture this area under the curve. That turns out to be expensive. And you can do Taylor series expansion. And that's one way that we're going to approach this. But we need to do it in a smart way. When we take derivatives of mesh-free approximations, because of the complexity of the shape functions, they end up being fairly expensive. Okay, let's look at this for thermoelasticity. Okay, very simple half plane problem. Okay, look at the displacement and temperature over time. I believe this is a quasi-static problem. And you can see that the displacement and temperature are getting unstable very, very quickly. Okay, if you keep running this, you'll find out that the displacements and temperature fields, the solution should be order 1 about. They get up to 10 to the 40th, 10 to the 43. Okay, so they're just getting absolutely unstable in time. Well, the instability in space is just growing and growing in time, I should say. And this is way worse than for pure solid problems. So this is pretty interesting here. Usually the instabilities, like the ones I showed for the Poisson equation, they're on the order of the solution themselves. This is 40 orders of magnitude larger than the solution itself. So this is just going to give you absolutely unacceptable results, and you'll definitely have to do something in this coupled problem. So this is something that's pretty interesting that we found out in this research. Okay, so we're going to take the approach that we previously developed called naturally stabilized nodal integration. The idea is fairly simple. Do a Taylor series expansion on the nodal strains, or in each nodal domain, about the centroid of the nodal domains. So we'll just truncate it to first order. Usually we use linear basis, although you can do higher order, but then you'll have to do a higher order Taylor series expansion. Gary Baslow's has some papers on that recently that you can read about. But we're going to stick to linear here. Okay, here's the stabilized strain energy. So what happens is I plug this into the bilinear form, right? And as you can imagine, these odd terms, so if I have the product of this and this after I plug this in, these odd terms are going to drop out. I'm left with nothing but even terms and this constant term. So the constant term I'm showing here in the first term, A sub D. So this is just the nodal strains. And then the additional term is those even terms. So I end up getting these quadratic products like x minus x sub L squared and so forth. And those are going to be inducing some stabilization. You can see that this type of term here is coercive, right? It's adding stability. Now we call this naturally stabilized nodal integration because these terms here are nothing but the moments of inertia. So you can consider it that it's a very natural way to do stabilization. Okay, we did the same thing for the temperature field now. So we look at the gradient of the temperature field. In a more general case, you could do the gradient of flux if you have a nonlinear law for your temperature field. But if you have a linear problem, like I'm showing here, we'll just do a Taylor series expansion with the gradient of the temperature field, and you do something very, very similar. You get the moments of inertia here, and then this coercive term for your stabilization in conjunction with the nodal terms. So this is a stabilized nodal integration. Okay. Now we need to avoid taking those derivatives if we want to keep things less expensive. So we'll try to do that in a, try to do it in a smart way. Okay, and the idea is this: there's something called implicit gradient, developed in the reproducing kernel literature, also known as synchronized derivatives. But you can show that they satisfy this property, is that I reproduce not the polynomial itself anymore. I reproduce it up to nth order for the gradient of that polynomial or monomial shown here. Okay, so this is the essential property that I want in my gradients, the completeness of the gradients. And I will just enforce that directly on some kind of function that we'll construct just like we did for the RK shape function. Okay, it turns out if you do that, then you get a form like this. So this is the so-called implicit gradient shape function. Okay, let's look at the standard reproducing kernel shape function. Okay, the standard one has this h naught term. So this is like 1, 0, 0, 0, however long your h is. Okay, the implicit gradient has this term. Okay, what does it have? Instead of the 1, 0, 0, 0, it will have this form, depending on the type of gradient that you want to approximate. I is the direction of the gradient. Okay, so you just put -1 here, here, or here, depending on the direction of the gradient. So I just replace this constant vector with this constant vector, and then I can reproduce gradients with nth order completeness. So the takeaway is this: I compute this anyway. Shape function. Okay, if I want to do stabilization, then I'll compute this. Right, so all I have to do, store this part, and then I'll just take this product to get an approximation of the gradient. So this ends up being essentially no cost. And compared to stabilization, where you have a lot of points like stress point type methods, then it'll speed up the simulation 10 to 20 times on paper if you do an operation count analysis. So we showed that in some earlier work. So quite an improvement. Okay, so I mentioned for this patch test correction, you can actually correct any type of numerical integration. So what we end up doing is correcting that stabilized nodal integration. And you can see this is just a verification, and we can still pass this patch test using the correction for the stabilized nodal integration. And we do this for thermoelasticity now. Okay, so let's look at some benchmarks. Okay, so you can see this is the result I showed before, just getting completely unstable in time. Here's NSNI, you can see it provides quite stable results. Okay, let's look at the accuracy. If you do stabilization just by itself, and you test like a non-uniform discretization, kind of a challenge problem, but you'll have that if you're in a real engineering problem. Okay, just do that. You can see that I do not capture the solution very well. The black is the analytical solution for coupled and uncoupled cases. Okay, so this is basically to show that I will need both. I will need the VC correction and I will need the stabilization if I want a stable and accurate solution. So I think this is a nice demonstration my student came up with. Okay, that was for a static problem or quasi-static problem. We can look at dynamic problems. So for the uncoupled case shown here, there's an analytical solution, which we agree pretty well. And then the coupled case, there's no analytical solution, so we compare with numerical solutions. You can see we agree quite well. Okay, so that's been developed pretty well, I would say. There's plenty more examples in the papers I referenced, but now we come to trying to do explicit time integration. Okay, so just to remind you again, we have this time step restriction for the parabolic energy equation. So generally explicit is considered prohibitively expensive because of this delta x squared. So I asked my student to look into if there's such thing as a hyperbolic energy equation. And in that case, indeed there is. And what we get, as you probably know, if you lump all of these, you can treat them, for hyperbolic equations, you get a time step like this. For the, for solids, it's the wave speed here. Turns out if you have a hyperbolic energy equation, you have a speed of thermal waves. And this is your time step restriction. So there are indeed hyperbolic energy equations, and the explanation is simple. The parabolic one has an infinite wave propagation speed, which is physically unacceptable from special relativity. Nothing can travel faster than light. Okay, so researchers actually looked into different theories with a second sound speed, which is the thermal speed of thermal waves. Okay, so there's actually plenty of literature explaining this, and for numerical purposes, this actually is quite convenient. But again, we don't want to violate the physical laws either. Okay, so we tested several of those theories. I'm just showing one, Green and Lindsay here. Okay, for the uncoupled and coupled cases. Very typical for the coupled case, we don't have an analytical solution, so we look at numerical solution from the literature. You can see we agree quite well in both cases. Oh, I guess we don't have an analytical solution here, but we agree with FEM and BEM. Okay, so you have the second sound speed. If you go and look into this, you'll find that people don't actually measure this for most materials, like metal, engineering material. Usually it's for superfluids, close to absolute zero, right? Some conditions that you don't normally have. For materials you don't usually have in engineering. So we looked at this, setting the second sound speed equal to the first sound speed, which I'm denoting C and C here. And let's just see what happens, right? Is this something we can do? Well, it turns out that you get results very close to the classical theory when you do that. It turns out that this, like the relaxation time in some of the theories, is very, very small, so that you get something very close to the classical theory. Okay, so obviously this depends on the problem constants. So this might be true, might not be true for some materials, but at least for several materials that we tested, a lot of engineering materials, this works out great. You get results very close to the classical theory. Okay, here's the Lord and Schulman hyperbolic theory. Here's the Green and Lindsay hyperbolic theory. Turns out you can do it for both and get results very close to the classical theory. Okay, now the takeaway is this: you get one time step for your solver. Okay, so if you have an explicit solid solver, you can implement this in a very practical way, right? You get one explicit time step to do the simulation. You do everything in an explicit manner, both the solid and the thermal field, and you still get results consistent with the classical theory. So this, I feel, is very practical. And in fact, we've implemented this and it is very practical, especially from an implementation standpoint and from an engineering standpoint, right? Because I don't have this second sound speed for most materials anyway. Okay, you can easily extend this to finite strain thermoplasticity. So this is a necking problem of an elastoplastic bar, just a half model here. You can see we agree pretty well with the reference. Here's the experimental data for this problem, the dotted markers here. You can see we agree pretty well for the reduction in necking region and then also force displacement. Okay, we have a reference, I believe, CMO FEM result. You can see we agree pretty well for the evolution of the temperature field. Okay, how about that second sound speed? Now we have a real material. We're going to set them equal to each other for the elastic and the thermal, and you can see, well, our results basically overlap for parabolic and hyperbolic. So this is kind of confirmation of what I mentioned before. Okay, I'll just show real quick. If you actually want to implement this, here's a, predictor corrector, everything that I would normally do in explicit dynamics for displacement. And well, we get the exact same scheme for the temperature field. So you can literally copy paste, chunks of your code and implement this in a very nice way into an existing solver. All right, let's look at thermoplastics now. So, I have my student look into all these details. You have shear thinning material. Okay, so we use power law model. We modify that with the Arrhenius law to incorporate the temperature effect. So fairly simple, but this ends up working pretty well. Okay, he dug up all these nice analytical solutions for thermal flow. Which, believe it or not, we have it for these non-Newtonian fluids with thermal flow and so on. So did a good job digging these up. So you can see we agree quite well. Here's another problem with the plate moving. You can see we agree quite well with the analytical solutions. And then you can actually combine a lot of these analytical solutions and verify something like the flow in the liquefier in the 3D printer, and actually derive an analytical solution here. So you can see we agree quite well there. Okay, how about turn the thermal part off and just try to do a large deformation non-Newtonian simulation. So here you see that we agree quite well with a couple reference solutions, volume of fluid, and I think this is improved SPH. Okay, so we have some confidence in our model, so we'll go to do the real thing. And as my students always find out when they do the real application, there's a lot of details you'll have to take care of, okay? So you have to apply the surface tension on these guys to get the right result. Heat convection with the ambient air, heat transfer with the bed. So yeah, as you probably know, if you try to simulate some of these type of real world problems, there's a lot of details you have to take care of. All right, so here's the result for one bead or road. We're doing this specifically because we have a solution that we can compare to. So here's the evolution of temperature over time. Here's our reference solution. I believe this is FEM, and for one road or bead, you can do FEM. So here we're basically just trying to verify our formulation for now and do validation do validation later, but for verification purposes, you can see our temperature drops and so forth match the reference pretty well. Actually, the physical contact angle agrees with the theory quite well. Okay, and then you can do numerical experiments like my collaborators are interested in, right? Different speed of the bed, or the extrusion rate, right? And as you can imagine, those should be about the same to get a nice smooth road. But now you have a framework to test those things. Okay, how about 3D printing? Turns out this is a viscoplastic fluid, or it's actually not really fluid or solid. It's got rheological properties. So a popular model is the Bingham fluid, which has a yield stress, and then it'll flow in a non-Newtonian manner after that yield stress. And it turns out that you have to use regularized models, right? You have a kind of step function here, which causes some numerical problems. So you actually have to use regularized type models. My experimental collaborators do a lot of calibration to get the parameters of these models. So I'm showing some of those details here. Here's a rheometer that they're using. Okay, from the numerical standpoint, we want to test that we get the right solution. So this is a dam break, and here's the leading edge, and then leading edge over time. So we verify with the experiment, but also some numerical solutions. You can see we agree quite well. Let's see, slump test. Turns out there's some analytical solutions, but you have to make some assumptions. So these solid lines are the assumptions on the flow. And then we also look at a reference solution, since these analytical solutions have a lot of assumptions, so are various assumptions. So we're in the ballpark here. Turns out that maybe this wasn't the best verification problem, but that's fine. Okay, now let's do the real thing. So here I'm just showing six cases, although we do, a lot more problems than this, but let's keep it simple. 6 cases, different printing speeds, extrusion speeds. Here's kind of the modeling domain that we're considering, and here's a profile and top-down view of the numerical result. Okay, it turns out, much like the thermoplastics, you got to pay attention to a lot of these details, right? You could prescribe the outlet velocity. You could prescribe it, with a parabolic solution that you think it would probably have, or maybe you give it some space and so forth. It turns out that this last modeling choice gives you the best result. Okay, so here's a typical simulation of, again, one bead. We're doing kind of a parametric study, so we're just looking at all these kind of cases. The dashed line is experimental. You can see that measured several, and then these are actually a few different material models that we tested. You can see we agree quite well across the variation on all these cases for different printing speeds and extrusion speeds, also different heights of the nozzle. Okay, so we came up with a stable, convergent, and efficient framework for nodal integration for hyperbolic heat conduction, which is also very nice for the explicit time integrator. It agrees with the classical theory, at least for all the materials that we've tested. So very nice to implement into an existing solver. I'll just mention now, we were showing about 1 bead for all these simulations, but we need to get into minutes and meters to do the real deal, right? So we probably need to go implicit, but there's some things like, we have specialized contact algorithms for meshfree. I'm not sure if anyone has, linearized those things. Do we need to do, say, massively parallel? We're going to do minutes and meters, and then we're also doing something called semi-Lagrangian. We're recomputing the shape functions all the time, and I think we need to do probably coupled Lagrangian, where you save the shape functions. It's very efficient, coupled with semi-Lagrangian, which has these large deformation capabilities. So there's some recent work by J.S. Chen. It's very nice. That has kind of arbitrary coupling domains, and we're looking into different schemes to do that. So thank you for listening to my talk, and I'll be happy to discuss the contents of this talk.